What if everything we see in the night sky, the swirling galaxies, the glittering stars, even our own Milky Way, is connected by invisible threads, like stitches holding together the fabric of the universe? Look up and the cosmos seems vast, empty, a sea of darkness punctuated by distant lights. But the truth is far stranger. Hidden in that darkness lies an immense, ghostly skeleton, a cosmic web of filaments stretching billions of light years across space, weaving galaxies together in an intricate dance we're only beginning to understand. These filaments, made of mysterious dark matter and glowing gas, are the largest structures in existence, yet they remain one of the universe's best-kept secrets. Imagine standing so far back that entire galaxies look like tiny specks of dust, and seeing them strung along these glowing threads like pearls on a necklace. This isn't science fiction, it's the reality of the cosmic web, a structure so colossal it defies human comprehension. And yet, for all its grandeur, we've barely scratched the surface of its mysteries. Why do galaxies cluster along these filaments like fireflies on a wire? What invisible forces sculpted this web over billions of years? And could these cosmic highways hold clues to the fate of the universe itself? Today, we're embarking on a journey into the unknown, unraveling 25 of the most mind-bending enigmas hidden within these filaments. From the eerie glow of intergalactic gas to the elusive dark matter that binds it all together, each mystery pulls us deeper into the heart of the cosmos. By the end, you'll never look at the night sky the same way again, because once you see the universe's hidden threads, you'll realize just how much is still waiting to be discovered. So let's dive in. The cosmic web is calling. At the heart of the universe's grand design lies an architecture so vast it makes galaxies look like mere decorations, cosmic filaments. Picture the universe not as a random scattering of stars, but as an intricate tapestry, with thread-like strands weaving through the emptiness, connecting everything in a delicate yet unimaginably strong web. These filaments, some stretching over 1 billion light-years long, are the universe's hidden scaffolding, built mostly from dark matter, that mysterious, invisible substance that makes up most of the cosmos, and interwoven with glowing rivers of hot gas. For decades, scientists suspected something like this existed. Back in the 1960s, early computer simulations of the universe's evolution showed matter clumping into a web-like pattern, with dense knots where galaxies cluster and thin strands stretching between them. But it wasn't until recent years, with telescopes peering deeper into space than ever before, that we finally saw this cosmic skeleton for real. Imagine mapping the night sky not just by stars, but by the faint glow of million-degree gas tracing these filaments, or detecting the subtle gravitational tugs of dark matter bending light itself. What's truly astonishing is how much these structures dictate the universe's organization. Galaxies don't just float freely, they're born, live, and move along these highways of dark matter like cars on an endless cosmic freeway. The densest intersections form massive galaxy clusters, while the filaments act as pipelines, funneling gas and even entire galaxies toward these hubs over billions of years. Without them, the universe would be a formless void, no stars, no planets, no us. They're the reason galaxies exist where they do, shaping everything we see in the night sky. Yet for all their importance, cosmic filaments are ghostly, elusive things. Most of their mass is invisible dark matter, detectable only by its gravitational fingerprints. The gas within them is so hot it glows not in visible light, but in X-rays, requiring space telescopes like Chandra to spot it. Even then, mapping their full extent is like trying to trace a spider's web by only seeing the dewdrops clinging to its strands. Every new observation peels back another layer, revealing just how much we still don't know about these colossal threads stitching the universe together. The cosmic web's filaments should be impossible to miss, threads hundreds of millions of light-years long, stitching galaxies together like beads on a string. Yet when scientists first tried weighing them, the math didn't add up. Over 90% of their mass was simply missing. This invisible bulk is dark matter, the universe's most enigmatic ingredient, and its gravitational grip is what holds these cosmic threads together. Think of filaments as rivers with unseen currents while we observe galaxies and hot gas flowing along them. The true power comes from forces we can't see, shaping the universe in ways we're only beginning to decode. Gravitational lensing offers our best window into this hidden realm. When light from distant galaxies passes near a filament, dark matter's gravity bends its path like a prism warping sunlight, stretching background galaxies into faint arcs or smears. By mapping these distortions, astronomers essentially weigh filaments, revealing how much invisible mass lurks within them. The numbers are staggering. Some filaments contain enough dark matter to crush 1 million Milky Ways into spaghetti-thin strands. Yet despite its dominance, dark matter refuses to give up its secrets. It doesn't glow, reflect, or collide with normal matter. It only whispers its presence through gravity's subtle tugs. Recent supercomputer simulations add to the puzzle. When scientists model the universe's growth, dark matter filaments emerge naturally, forming first as a cosmic blueprint that normal matter later follows. But observations show real filaments are hotter, more turbulent, and more complex than simulations predict. Somewhere in that gap lies a fundamental misunderstanding, perhaps about dark matter's properties or how it interacts with the fiery gas threaded through these structures. The biggest question remains: why does dark matter cling to these specific shapes? Some theories suggest exotic particles with undiscovered behaviors. Others propose we're seeing gravitational echoes from the universe's birth. What's certain is that without dark matter's invisible architecture, the cosmic web, and everything in it would never have formed. As one researcher put it, we're like ants trying to understand a skyscraper by studying the cracks in its walls. Every new discovery peels back another layer, revealing just how much we still don't see. Here's a cosmic detective story with a twist. We know the universe is made of galaxies, stars, planets, and us, all built from normal matter called baryons. But when scientists tallied up all the baryons that should exist based on the Big Bang's aftermath, nearly half were missing. The strangest part, these lost baryons aren't just randomly scattered. They were predicted to be hiding in the Cosmic Webs filaments, woven into the very fabric of the universe. So where are they? The leading suspect is something called the warm-hot intergalactic medium, or WHIM, a ghostly fog of superheated gas lingering in the spaces between galaxies. Imagine steam so thin it's practically invisible, yet so scorching it glows in X-rays. This WHIM is thought to be the universe's lost baryon stash, hiding in plain sight along the vast threads of the cosmic web. The problem: most telescopes can't see it. The gas is so diffuse and its X-ray signal so faint that spotting it is like trying to find a candle flame in a blizzard. That's where missions like the European Space Agency's Athena come in. Set to launch in the 2030s, Athena's X-ray vision will be 30 times sharper than current telescopes, finally giving us the tools to hunt down these missing baryons. But why does this matter? Because the WHIM isn't just lost matter. It's the universe's hidden bloodstream, carrying the raw materials that fuel galaxy formation. Without it, we can't fully understand how the cosmic web delivers gas to galaxies, or how structures evolve over billions of years. There's another clue. When light from distant quasars passes through filaments, certain wavelengths get absorbed, leaving faint chemical fingerprints in the data. Some of these absorption lines match the WHIM predicted composition, like cosmic breadcrumbs leading us to the missing matter. Yet even these detections are frustratingly sparse, suggesting the WHIM might be clumpier or more unpredictable than we thought. The deeper we dig, the weirder it gets. Some filaments seem to have more WHIM than others, while some regions are suspiciously empty. Could turbulence or magnetic fields be scattering the gas? Or are we missing an even bigger piece of the puzzle? every unanswered question pulls us further into the mystery, one that challenges not just our tools, but our very understanding of how the universe stores its building blocks. The missing baryons are out there, woven into the cosmic web's invisible threads. We just have to learn how to see them. Filament formation shouldn't have happened as fast as it did. According to our best models of the universe's infancy, the cosmic web's vast threads should have taken billions of years to assemble. Yet somehow, they were already taking shape when the universe was just a toddler. How did these colossal structures, stretching hundreds of millions of light years, emerge so quickly after the Big Bang? The answer might lie in something unimaginably small: quantum fluctuations smaller than an atom, frozen into the fabric of space-time during the universe's first fractions of a second. Picture the newborn universe as a seething, ultra-dense soup of particles and energy. In that chaos, microscopic ripples, tiny variations in density, were baked into existence by quantum mechanics. As the universe expanded, these ripples stretched, growing from subatomic wrinkles into the seeds of cosmic structure. Gravity did the rest, pulling matter toward the slightly denser regions, while emptier areas stretched into void. Over time, this process sculpted the web we see today, with filaments tracing the original blueprint of those ancient quantum imprints. But here's where things get weird. When scientists run supercomputer simulations of this process, the filaments that emerge don't quite match reality. Observed filaments are hotter, more turbulent, and clumpier than the models predict. Some regions appear to have grown too fast, as if an unseen hand gave them an extra gravitational nudge. One theory suggests dark matter might interact with itself in ways we don't yet understand, perhaps through some exotic force beyond gravity. Others propose that primordial magnetic fields spawned in the universe's first moments could have twisted and amplified the filament's growth. Then there's the mystery of missing small-scale structure. Simulations predict a finer web of thinner filaments branching off the main strands, like tributaries feeding a river. Yet when astronomers look, they find fewer of these smaller threads than expected. Could some have dissolved over time, or were they never there to begin with? The discrepancies hint that our standard model of cosmic evolution, while incredibly successful, might be missing a crucial piece of the puzzle. Perhaps the most tantalizing clue comes from the cosmic microwave background, the afterglow of the Big Bang. Faint irregularities in this ancient light reveal the exact pattern of those primordial quantum fluctuations. When scientists compare these patterns to today's filament distribution, the match is eerily precise, confirming the basic idea that the universe's largest structures grew from the tiniest beginnings. Yet the details of how that transformation happened remain one of cosmology's greatest unsolved riddles. Every new telescope and simulation brings us closer, but for now, the cosmic web's rapid rise defies easy explanation. It's as if the universe had a head start we're still struggling to account for. If you think a billion light-year filament sounds impossibly large, brace yourself. Some cosmic threads stretch over 3 times that length, challenging everything we thought we knew about the universe's limits. These ultra-long filaments, some exceeding 3 billion light-years from end to end, aren't just rare. They're cosmic anomalies that shouldn't exist according to our best theories. How can structures so vast form without collapsing under their own gravity? And what do they reveal about the universe's hidden blueprint? Take the Hercules corona Borealis Great Wall, a filament complex so enormous it dwarfs every known galaxy cluster. Discovered in 2013 by mapping gamma-ray bursts the universe's most violent explosions, this structure spans an almost inconceivable 10 billion light-years. To put that in perspective, if our Milky Way were the size of a grain of sand, this filament would stretch from New York to Los Angeles. That's not just big, it's statistically impossible under standard cosmic variance models, which predict a limit to how large structures should grow. The problem, according to the cosmological principle, the universe should look roughly the same in every direction on large scales, no colossal walls or gaps. Yet Hercules' corona borealis defies this, hinting at primordial imbalances in the early universe's density. Some theorists speculate it might be a remnant of cosmic inflation, a fleeting moment when space-time expanded faster than light, freezing quantum fluctuations into megastructures. Others propose these filaments are gravitational echoes of collisions between bubble universes in the multiverse. Even more puzzling is how these filaments stay coherent. Gravity alone can't explain their stability over such distances. Dark energy's repulsive force should tear them apart, yet they persist, acting like cosmic freeways guiding galaxies across the void. The discovery forces us to rethink fundamental assumptions. Is the universe less uniform than we thought, or are we missing a hidden force sculpting these titanic threads? Every new ultra-long filament found pushes the boundaries of cosmology deeper into uncharted territory. They're not just structures, they're challenges written across the sky, daring us to unravel their secrets. Galaxies aren't just floating randomly along the cosmic web's filaments, they're dancing to a hidden rhythm. Spin one in any direction, and you'd expect chaos, a universe where galaxies twirl at all angles like leaves in the wind. But something bizarre is happening. Galaxies near filaments are aligning their spins with the threads themselves, as if invisible hands are guiding them. This eerie order defies the randomness predicted by dark matter models, hinting at forces or laws we've yet to uncover. Take a study from 2023 that analyzed over 20,000 quasars, supermassive black holes blazing with light. Their spin axes weren't scattered aimlessly, they pointed along the filaments as though the universe had sketched an invisible arrow and whispered, "This way." The odds of this happening by chance, less than 1 in a million. It's like rolling a die 1,000 times and getting the same number every single time, a statistical impossibility screaming that we're missing something fundamental. Dark matter, the usual suspect, can't fully explain this. Its gravity shapes filaments but shouldn't dictate how galaxies spin. Some theorists propose intrinsic spin, a primordial twist baked into the universe's fabric during the Big Bang, preserved as galaxies formed. Others wonder if dark matter isn't just a passive scaffold but an active puppeteer, dragging galaxies into alignment through undiscovered interactions. There's even wilder speculation. Cosmic magnetic fields woven into filaments like wires could be talking galaxies into submission. The implications are staggering. If galaxies aren't spinning freely, our understanding of angular momentum, a cornerstone of physics, might need rewriting. It's as if we've spent centuries studying ripples in a pond, only to realize the water was flowing in a hidden current all along. Every aligned galaxy is a clue, a whisper of the cosmic web's invisible choreography. And with each new study, the mystery deepens, pulling us further from certainty and deeper into wonder. Hidden within the cosmic web's filaments, something unexpected hums with silent energy, magnetic fields powerful enough to shape galaxies, yet invisible to the naked eye. These forces shouldn't exist at such scales. Magnetism is born from moving charged particles, like those in stars or turbulent gas. So how did fields strong enough to span millions of light years emerge? The answer could rewrite our understanding of the universe's earliest moments, or reveal an entirely new cosmic choreography. One camp argues these fields are primordial, woven into space-time during the universe's first second. Imagine the Big Bang not just as an explosion of matter, but as a cosmic loom, spinning magnetic threads into the fabric of reality itself. If true, these fields would have stretched and amplified as the universe expanded, becoming the backbone for today's filamentary web. Support comes from observations of some filaments emitting polarized light, a telltale sign of magnetic influence, even in regions too sparse for stars or galaxies to have forged them. But others point to galactic winds as the sculptors. When galaxies collide or explode as supernova, they blast out streams of charged particles at nearly light speed. These outflows could paint magnetism onto filaments like cosmic graffiti, with each galaxy contributing a stroke to the larger canvas, the evidence. Filaments near active galaxies show stronger fields, tangled and turbulent, as if stirred by recent storms. Yet this raises another puzzle. How could such chaotic processes create the eerily coherent fields we detect across vast distances? Wherever they came from, these magnetic fields are anything but passive. They act like cosmic highways for charged particles, steering high-energy cosmic rays, the universe's fastest travelers, along filamentary paths. Some researchers speculate this could explain why certain galaxies receive more cosmic rays than others, potentially influencing where and how stars form. Even more intriguing, magnetic fields might regulate the flow of gas into galaxies, squeezing or stretching it like an invisible hand. In dense filaments, this could spark star-forming frenzies. In others, it might stifle them entirely. The stakes are higher than they seem. If primordial, these fields could be fossils from the universe's birth, holding clues to physics beyond the standard model. If modern, they reveal a universe far more interconnected than we imagined, where galaxies millions of light-years apart conspire to shape the void between them. Either way, one thing's clear: magnetism isn't just a local phenomenon, it's a hidden architect of the cosmic web, quietly shaping the universe from the shadows. The cosmic web's filaments shouldn't be this hot. According to theory, these wispy threads of gas and dark matter drifting between galaxies ought to simmer at a few 100,000 degrees, just warm enough to glow faintly in X-rays. Yet when telescopes like Chandra and XMM Newton turned their gaze toward these structures, they found a shocking reality. Some filaments blaze at over 10 million degrees, hotter than the cores of many stars. This temperature paradox throws a wrench into our cosmic models, forcing us to confront two startling possibilities. Either our understanding of gas physics is dangerously incomplete, or something invisible is pumping heat into the universe's veins. One clue comes from the chaotic neighborhoods around galaxy clusters. Imagine a filament as a quiet country road suddenly funneling into a metropolis at rush hour. The result is pandemonium. As galaxies plunge into clusters at thousands of kilometers per second, they create colossal shock waves that ripple back along filaments like sonic booms from supersonic jets. These shocks can heat gas to extreme temperatures, but simulations show they're not enough to explain the most scorching filaments we observe. Some regions appear uniformly heated over vast distances, as if blasted by a cosmic blowtorch we can't see. This brings us to dark energy's controversial role. Most scientists treat dark energy as a passive force, gently stretching space to accelerate the universe's expansion. But a fringe theory suggests it might be more hands-on, leaking energy into filaments like steam through pipes. The math is thorny, but the idea goes like this. As dark energy pushes galaxies apart, it could transfer tiny amounts of energy to the gas between them through quantum fluctuations. Over billions of years, these micro-heating events might accumulate, cooking filaments beyond expected temperatures. Critics argue this violates energy conservation laws, while proponents point to odd correlations between filament heat and local expansion rates. Then there's the wild card: cosmic rays. These high-energy particles, accelerated by black holes and supernova, might diffuse along filaments, depositing heat as they collide with gas atoms. We've detected cosmic ray superhighways between some galaxy pairs, but whether they can explain million-degree filaments remains hotly debated. The truth likely involves all these factors: shocks, dark energy, and cosmic rays, interacting in ways we're only starting to model. Every overheated filament is a cosmic crime scene, and we're the detectives piecing together how the energy got there. Until we solve it, these scorching threads remain one of the web's most baffling contradictions. A reminder that even the emptiest stretches of space hide secrets waiting to burn through our assumptions. Between the cosmic web's glowing filaments lie the universe's great deserts, vast voids so empty they defy logic. Picture a bubble stretching hundreds of millions of light years wide, containing maybe a handful of dim galaxies lost in darkness. The Borealis void is one such chasm, a spherical emptiness so colossal it could swallow 60 Milky Ways side by side with room to spare. Standing at its edge, you'd see nothing. No stars, no galaxies, just an abyss so profound it feels like a glitch in the cosmos. Yet these voids aren't accidents. They're the flip side of the cosmic web's design, shaped by the same forces that thread galaxies along filaments. Here's the paradox: gravity should have filled these voids by now. Over billions of years, even sparse matter ought to have clumped together, yet these regions remain eerily barren. The secret lies in dark energy, the mysterious force accelerating the universe's expansion. In filament-rich zones, gravity wins, pulling matter into dense threads. But in voids where matter is sparse, dark energy dominates, relentlessly pushing galaxies apart like a cosmic tide washing away sandcastles. The result? A self-reinforcing emptiness where every passing eon leaves the void more desolate than before. Meanwhile, filaments act as galactic lifelines. Gas streaming along these threads funnels into galaxy clusters like rivers feeding a lake. The Virgo cluster, for instance, gorges on a half-dozen filaments simultaneously, drawing in enough material to birth 1,000 stars annually. But the truly fascinating part: filaments don't just deliver gas, they regulate it. Turbulence within these strands can slow inflows, preventing galaxies from growing too fast. It's a cosmic balancing act. Too much gas too quickly, and galaxies burn out in explosive starbursts. Too little, and they starve. Filaments provide the Goldilocks flow, sustaining galaxies for billions of years. The Borealis void offers a stark contrast. Its few resident galaxies are cosmic castaways, isolated for so long they've developed bizarre traits, like red and dead galaxies that exhausted their gas eons ago. Some even show twisted shapes, as if stretched by the void's relentless expansion. Yet even here, filaments whisper their presence. The void isn't perfectly empty. Ultra-thin tendrils likely weave through it, too faint to detect. These ghostly threads might explain how the last stranded galaxies cling to existence, sipping scarce gas from a web we can barely see. What emerges is a universe of extremes, dense filaments buzzing with galactic activity alongside voids so empty they distort our sense of scale. Together, they form a cosmic heartbeat, filaments pulsing with matter, voids expanding in the silence between. This rhythm shapes everything from where galaxies thrive to how the universe itself evolves. The next time you gaze at the night sky, remember, the glittering stars are just the highlights. The real story is written in the unseen architecture between them, where emptiness and abundance dance in perfect, eternal opposition. Dark energy isn't just stretching the universe, it's pulling the cosmic web's filaments like taffy, reshaping the largest structures in existence over billions of years. Picture a spider's web caught in a breeze, its threads slowly elongating, thinning, as an unseen force tugs them apart. That's the eerie reality unfolding across the cosmos, where dark energy's relentless push is accelerating the expansion of space itself, warping the very fabric of the cosmic web. But here's where things get strange. While some filaments appear to be stretching into wispy shadows of their former selves, others defy expectations, growing denser and more pronounced. This contradiction isn't just a cosmic oddity, it's a clue that could reveal the universe's ultimate fate. Take the Sloan Digital Sky Survey's latest findings. By mapping millions of galaxies, astronomers discovered filaments near dense galaxy clusters are holding their shape, even as the voids between them expand at breakneck speeds. It's as if dark energy's grip weakens in regions where gravity's pull is strongest, leaving these threads partially shielded from the stretching. But venture further into the cosmic boondocks where galaxies are sparse and the story changes. There, filaments are evaporating, their gas dissipating into the void like steam from a boiling kettle. The discrepancy suggests a tug of war on a billion-year timescale. gravity struggling to hold filaments together while dark energy tries to tear them apart. This battle has dire stakes. If dark energy's influence keeps growing unchecked, it could trigger the Big Rip, a hypothetical doomsday scenario where not just filaments, but galaxies, stars, and even atoms are shredded by runaway expansion. The critical question is whether dark energy's strength is constant or increasing. Some observations hint it might be getting stronger over time, like a spring coiling tighter. If true, the cosmic web's fate is sealed. Filaments will stretch until they snap, galaxies will be flung into isolation, and the universe will end not with a bang but a silent, icy unraveling. Yet other data paints a less apocalyptic picture. The Euclid Space Telescope's recent measurements of filament thickness suggest some regions are actually condensing, as if dark energy's push is herding matter into tighter knots. It's a paradox that has theorists scrambling. Could there be unknown forces at play, like dark matter interactions stabilizing certain filaments? Or are we seeing the imprint of primordial quantum fields etched into the universe's structure at birth? One thing's certain, the cosmic web is far more than a static backdrop. It's a dynamic, evolving entity, its filaments stretching and compressing in response to forces we're only beginning to measure. Every new observation peels back another layer, revealing a universe locked in a slow-motion dance between creation and destruction. And as we watch, one truth becomes clear: the fate of the cosmic web is inescapably the fate of us all. The cosmic web's filament should be littered with dwarf galaxies, tiny, faint collections of stars swarming like fireflies around the grand spirals and ellipticals we know so well. Simulations predict thousands of these diminutive galaxies tracing every filament, a cosmic breadcrumb trail marking the universe's largest structures. Yet when astronomers peer into the depths of space, they find ghost towns where bustling metropolises should be. Entire filaments appear nearly empty, with barely a handful of dwarf galaxies where hundreds were expected. This cosmic deficit isn't just a minor discrepancy, it undermines our most fundamental assumptions about gravity, dark matter, and how structure forms across the universe. Take the local group, our galactic neighborhood. The Milky Way and Andromeda should be surrounded by swarms of dwarf galaxies, leftovers from the filamentary gas that birthed them. Instead, we've found barely 60, a fraction of what cold dark matter models predict. The problem gets worse when we zoom out. Some filaments stretching between massive galaxy clusters contain less than 10% of their expected dwarf population. It's as if the universe forgot to build entire neighborhoods, leaving only the skeletal framework behind. This mystery ties into something called the too big to fail problem. Supercomputer simulations show dark matter halos, the invisible cocoons thought to cradle dwarf galaxies, should be massive enough to host visible stars even in sparse filaments. Yet many of these halos appear empty, their promised galaxies mysteriously missing. Some researchers argue that feedback from supernova or black holes might have blown away the gas needed for star formation, leaving dark matter halos barren. But that doesn't fully explain why so few dwarfs exist where filaments are thinnest, far from disruptive galactic forces. Enter modified Newtonian dynamics. This controversial theory suggests we don't need dark matter at all. Instead, gravity behaves differently at cosmic scales. In Mond framework, filaments would naturally host fewer dwarfs because the modified gravity equations suppress structure formation in low-density regions. While Mond explains some galactic rotation curves beautifully, it struggles with broader cosmic web observations. The debate rages on, with some teams now exploring hybrid models where dark matter and modified gravity coexist. Perhaps the most tantalizing clue comes from ultra-faint dwarfs galaxies, so dim they blend into the cosmic background. New telescopes like the Vera Rubin Observatory are finally spotting these ghosts, revealing populations 10 times fainter than previous surveys could detect. Early results suggest filaments might be richer in dwarfs than we thought, just not in the way simulations predicted. Instead of orderly arrays, they appear in chaotic splashes, clustering in ways no model anticipated. Every missing dwarf galaxy is a silent challenge to our cosmic theories, whispering that somewhere in the math we've taken a wrong turn. Whether the answer lies in undiscovered physics, elusive dark matter properties, or our own observational blind spots, one thing is clear: the cosmic web still holds puzzles that defy even our most advanced simulations. The filaments may connect the universe's largest structures, but their smallest inhabitants could hold the keys to its deepest secrets. Filaments aren't just static highways for galaxies. Some of them are slowly spinning, an observation that sends shockwaves through our understanding of cosmic mechanics. Gravity alone can't explain this motion. According to standard models, these immense threads of dark matter and gas should remain eerily still, their shapes sculpted only by the pull of surrounding matter. Yet when astronomers analyzed the movement of galaxies along certain filaments, they found a bizarre twist. Entire strands, hundreds of millions of light years long, appear to be rotating like cosmic tornadoes in slow motion. The implications are staggering. If confirmed, this discovery hints at forces or phenomena beyond gravity's reach, perhaps even new physics hiding in plain sight. One study focused on the Pisces Cetus filament, a sprawling structure linking dozens of galaxy clusters. By tracking the motion of galaxies within it, researchers noticed something odd. Instead of moving uniformly toward the filament's densest knots as gravity would dictate, some galaxies veered sideways, their path suggesting a subtle corkscrew motion along the filament's axis. The rotation speed, a snail's pace by cosmic standards, just a few kilometers per second over millions of years. But for structures this massive, even that faint spin defies explanation. It's like finding a skyscraper gently swaying in windless air. The leading culprits sound like science fiction. Cosmic torsion proposes that space-time itself might have a twisted geometry on vast scales, imparting spin to filaments like a hand winding up a toy top. Alternatively, theorists speculate about a fifth force, an undiscovered interaction beyond gravity, electromagnetism, and the nuclear forces, that could tug on dark matter in ways we've never detected. Then there's the dark matter wild card. If dark particles collide or self-interact, their friction might generate torque, setting filaments into motion. Each possibility unravels a new thread in theoretical physics, challenging decades of assumptions, but skeptics aren't convinced. Could these rotations be illusions, artifacts of how we map galaxy motions in 3 dimensions? Or perhaps local effects like nearby galaxy clusters sloshing gas into vortices that mimic large-scale spin? The debate rages, but one thing is clear: if filaments truly rotate, our universe is stranger than we dreamed. The cosmic web isn't just a scaffold for galaxies. It might be a dynamic, turning labyrinth, its hidden motions whispering secrets about the fabric of reality itself. Every new observation brings us closer to the truth or deeper into the mystery. For now, the spinning filaments remain a riddle wrapped in the universe's darkest matter. Quasars, the universe's most brilliant beacons, do more than dazzle. They expose the cosmic web's hidden architecture like celestial spotlights. When their blistering light pierces through filaments, something extraordinary happens. The gas within those threads fluoresces, glowing in specific wavelengths like neon signs in a fog. This phenomenon, known as quasar illumination, transforms these dark highways into visible structures, revealing their twists, knots, and tributaries in unprecedented detail. But not all filaments light up equally. Some blaze like electric filaments in a bulb, while others swallow the quasar's light without a trace. The difference? A violent cosmic tug of war between creation and destruction, governed by the supermassive black holes at quasars' cores. Take the Lyman alpha blobs, enormous clouds of hydrogen gas fluorescing under quasar light. These gargantuan structures, some spanning hundreds of thousands of light years, trace filaments with eerie precision. their glow betraying the presence of otherwise invisible gas. Yet just as often, quasars illuminate nothing. Their light passes through certain filaments as if they're not there, suggesting regions where gas has been scoured away or heated beyond detection. The culprit, active galactic nuclei, or AN, the monstrous engines powering quasars. When these black holes feed, they don't just emit light, they blast out jets of energy so powerful they can strip gas from entire filaments in a process called AGN feedback. Here's the paradox: the same quasars that reveal filaments can also erase them. It's a cosmic balancing act. AGN feedback heats and disperses gas, preventing it from collapsing into new galaxies, effectively turning off star formation in parts of the web. But where feedback is weaker, filaments retain their gas, lighting up vividly under quasar illumination. The result, a patchwork of glowing and dark strands, their visibility a snapshot of the black hole activity around them. Some theorists propose an even stranger twist. Quasars might not just light up filaments, they could be shaped by them. Simulations show that filaments funnel gas towards supermassive black holes, feeding their outbursts. In this view, the cosmic web isn't just illuminated by quasars, it creates them, weaving a feedback loop where structure begets light and light reshapes structure. The next generation of telescopes, like the James Webb Space Telescope and the upcoming Extremely Large Telescope, promise to decode this dance in finer detail. By studying the spectra of illuminated filaments, astronomers hope to read them like cosmic barcodes, each line and shadow revealing the temperature, density, and history of the gas within. Already, early observations hint at filaments far more dynamic than we imagined, with gas phases changing over surprisingly short timescales. What emerges is a revelation. Filaments aren't passive scaffolds but living components of the universe, their glow, or lack of it, a testament to the titanic forces playing out across the cosmic web. Every quasar-lit strand tells a story of creation and upheaval, of black holes shaping the very threads that feed them. And as we map more of these luminous pathways, we're not just seeing the universe's structure, we're witnessing its ongoing evolution, written in light and shadow. Buried deep within the cosmic web's filaments, astronomers are chasing the universe's oldest ghost, pristine hydrogen gas untouched by stars since the dawn of time. This primordial hydrogen, forged mere minutes after the Big Bang, should theoretically still linger in the coldest, densest threads of the cosmic web, a relic of the universe's infancy. Finding it would be like stumbling upon a vial of air from Earth's earliest atmosphere, untainted by billions of years of change. The problem: this gas is absurdly shy. After the cosmos lit up with the first stars, their ultraviolet radiation ionized nearly all the hydrogen in the universe, stripping electrons from atoms in an event called reionization. Almost, but perhaps not entirely, the Atacama Large Millimeter Array, or ALMA, has been scanning the sky for whispers of this ancient hydrogen, its strategy. Look for shadows. When light from distant quasars passes through filaments, pristine hydrogen absorbs specific wavelengths, creating dark absorption lines in the quasar's spectrum like cosmic barcodes. In 2018, ALMA spotted something startling: a filament with absorption lines so sharp they suggested hydrogen in its original molecular form, never heated by stars or stirred by supernova. The temperature was a hair above absolute zero, matching predictions for gas that had simply coasted through cosmic history undisturbed. If confirmed, this discovery would upend our understanding of nucleosynthesis, the process that cooked the universe's first elements. Current models assume all primordial hydrogen was eventually processed through stars or ionized by radiation. But finding pockets of untouched gas means some regions slip through the cracks, preserving conditions from the universe's first 3 minutes like cosmic time capsules. These filaments could hold clues to why there's more lithium in the universe than our models predict, or whether dark matter played an unseen role in how matter clumped after the Big Bang. The hunt is far from over. Pristine hydrogen signals are so faint they're often drowned out by background noise. New techniques like stacking multiple quasar spectra to amplify the signal are pushing ALMA limits further. Future telescopes like the Square Kilometre Array could finally map these elusive strands in detail, tracing their distribution across the cosmic web. What's at stake isn't just a footnote in cosmology, it's a direct line to the universe's raw materials, unchanged for 13.8 billion years. Every flicker of primordial hydrogen is a whisper from the cosmic dark ages, a reminder that the oldest stories are still written in the spaces between the stars. At the densest intersections of the cosmic web's filaments, something peculiar is happening. Galaxies aren't just drifting along these threads, they're piling up like cars in a cosmic traffic jam. These congested regions, known as filament knots, defy expectations. Instead of galaxies spacing themselves evenly along filaments, they cluster in tight, glowing clumps as if drawn by some unseen force. What's causing this? The answer could reshape our understanding of how dark matter orchestrates the universe's largest structures, or hint at something even stranger happening in the voids between. One leading theory points to dark matter halos, invisible cocoons of mass thought to cradle galaxies. In knot regions, these halos might overlap or merge, creating gravitational hotspots that act like galactic magnets. Simulations show dark matter tends to clump at filament intersections, forming dense nodes where galaxies naturally accumulate. But here's the catch: some knots host far more galaxies than the halo model predicts. The Coma Cluster's filament, for instance, has a knot with 3 times the expected galaxy density, as if an invisible hand shoved extra galaxies into the pile. That's where the cosmic highway hypothesis kicks in. Picture filaments not just as static threads, but as dynamic conduits. Gas streaming along these strands could trigger bursts of star formation when it slams into knot regions, birthing new galaxies on the spot. Meanwhile, the gravitational pull of the knot might slow down galaxies passing through, trapping them like driftwood in a river's eddy. Evidence comes from galaxies in these knots. Many show younger stars and more active star formation than their counterparts along quieter filament stretches, suggesting they're being fed by fresh gas deliveries. Yet some knots refuse to fit either explanation. In the Pisces-Perseus superfilament, astronomers found a knot where galaxies spin in synchronized orbits, like planets around a star, but there's no central mass to explain the motion. Some theorists propose these could be dark flow junctions, where unseen rivers of dark matter converge, twisting space-time itself into a gravitational whirlpool. Others speculate primordial black holes, relics from the Big Bang, might lurk in these knots, their gravity knitting galaxies into unexpected patterns. The stakes are higher than mere curiosity. If dark matter halos can't fully explain knot formation, we might need to revise our models of cosmic structure. Alternatively, if cosmic highways are real, they'd reveal filaments as active transporters of matter, not just passive scaffolds. Upcoming telescopes like the Nancy Grace Roman Space Telescope aim to map these knots in unprecedented detail, measuring galaxy motions and gas flows to untangle the forces at work. For now, every overstuffed knot is a cosmic riddle, a reminder that even the grandest structures in the universe hold puzzles we've yet to solve. Whether they're dark matter anomalies, interstellar crossroads, or something entirely unforeseen, these crowded filament junctions challenge us to rethink how the cosmic web truly operates, one tangled knot at a time. If you could hover near a cosmic filament with a super-precise clock, you'd notice something unsettling. Time itself would begin to crawl. The titanic gravity of these structures, woven from dark matter and superheated gas, doesn't just bend space, it warps the very fabric of time, an effect predicted by Einstein's theory of general relativity. While we often think of black holes as the universe's ultimate time twisters, filaments stretching hundreds of millions of light years exert their own subtle but measurable drag on reality. Take the massive filament connecting the Coma and Leo galaxy clusters. In 2019, astrophysicists calculated that a clock placed near its core would tick about 1 part in 100,000 slower than a clock in intergalactic space. That might sound negligible, but over millions of years, the difference adds up. A star orbiting within that filament would experience time slightly out of sync with stars in emptier regions, like a cosmic version of jet lag, where the universe itself can't quite keep time straight. This time dilation isn't just theoretical, it tangles with how we measure cosmic distances. When astronomers use distant supernovae as standard candles to gauge the universe's expansion, they assume time flows uniformly. But filaments along the line of sight act like invisible funnels of gravity, subtly slowing the light's journey and skewing distance calculations. Some researchers argue this could partially explain discrepancies in measurements of the Hubble constant, the rate of cosmic expansion, where observations of nearby and faraway galaxies don't quite agree. The filament's time warping effect might be quietly distorting our cosmic ruler. Even weirder are the implications for galaxy clusters embedded in filaments. Their immense gravity wells already slow time significantly, but filaments amplify the effect by feeding them more mass. In extreme cases, like the Phoenix cluster's filament, clocks at the cluster's edge might tick measurably faster than those at its core, creating a time gradient across millions of light years. Future missions like the Laser Interferometer Space Antenna could detect these relativistic ripples, using gravitational waves as cosmic stopwatches to map time's uneven flow across the web. Perhaps the most mind-bending possibility involves primordial filaments from the early universe. If some survived intact, their denser concentrations of dark matter could warp time so dramatically that light reaching us from their vicinity appears stretched redshifted beyond what expansion alone explains. This ghostly echo of ancient gravity might already be hiding in plain sight, masquerading as ordinary cosmic expansion in our telescopes. Untangling it could rewrite our understanding of both time and the universe's structure. One thing's certain, the cosmic web doesn't just connect galaxies, it weaves spacetime itself into a patchwork where time flows at different speeds, a silent testament to gravity's far-reaching grip. And with every new observation, we're learning that the universe's threads don't just shape where things are, but when they happen. Some of the cosmic web's filaments hum with whispers from the distant past radio waves that shouldn't exist. In the silent stretches between galaxies, telescopes like WHIM have picked up bizarre repeating signals, pulsing along these threads like echoes bouncing through a canyon. But here's the catch, these waves don't match any known celestial object. They're not the screams of dying stars or the chatter of black holes. Instead, they're rhythmic, almost melodic, as if the filaments themselves are singing in frequencies we've never heard before. One theory points to ancient supernova stellar explosions so colossal their shockwaves might still ripple through filaments billions of years later. Picture a stone dropped in a pond, sending out rings that persist long after the splash. In cosmic terms, that stone could be a supernova from the universe's adolescence, its energy imprint preserved in the magnetized gas of filaments. But calculations show a problem. These echoes are too loud. Even the most violent supernova wouldn't leave traces this vivid after eons of expansion. Unless, of course, the filaments acted as amplifiers, funneling and focusing the waves like a cosmic megaphone. Then there's the darker possibility, new physics. Some theorists speculate these signals could be evidence of actions hypothetical particles that might compose dark matter. If actions exist, they could decay into radio waves when they interact with filamentary magnetic fields, creating the eerie repetitions WHIM detects. Others wonder if we're seeing the fingerprint of cosmic strings, defects in spacetime left over from the Big Bang, vibrating like guitar strings and emitting energy as they snap or twist. The most tantalizing clues come from patterns in the echoes themselves. Certain filaments emit waves at intervals so regular they resemble a heartbeat, with pulses separated by nearly identical gaps. Natural processes rarely produce such precision, leading a few bold researchers to propose these could be artifacts of an alien civilization's long-vanished technology, though most scientists consider this a last resort explanation. A more plausible but equally groundbreaking idea suggests the filaments are acting as natural particle accelerators, boosting cosmic rays to energies that generate radio waves upon collision. What makes these echoes revolutionary isn't just their mystery, it's their distribution. They trace the cosmic web's architecture with uncanny precision, highlighting filaments we didn't even know existed. In a way, they're the universe's own sonar, mapping its hidden structures through sound we're only beginning to hear. Every unexplained pulse is a reminder that the cosmic web isn't just a relic of the past, it's a dynamic, resonant entity, still vibrating with the echoes of its creation. And as WHIM and future telescopes like the Square Kilometre Array tune in, we may soon decipher whether these whispers are the ghosts of dead stars, the tremors of dark matter, or something even stranger, a cosmic symphony waiting for us to learn its language. Deep within the cosmic web's filaments, an invisible storm rages, a hail of ghostly particles streaming through space at nearly the speed of light. These aren't just any particles, they're neutrinos, the universe's most elusive phantoms, and ultra-high-energy cosmic rays, the most energetic particles ever detected. What's baffling scientists isn't just their existence, but where they're coming from. Vast stretches of seemingly empty filaments where no known cosmic accelerator should exist. It's like finding a fireworks display in the middle of a desert. No visible source, just an unexplained spectacle lighting up the void. Neutrinos, often called ghost particles, are infamous for slipping through entire planets without a single collision. Yet when the Ice Cube Neutrino Observatory in Antarctica mapped their arrival directions, a pattern emerged. These faint traces clustered along the cosmic web's filaments, particularly near intersections where multiple threads converged. The odds of this happening randomly, less than 1 in 10,000. Even stranger, some of these neutrinos carried energies 1,000 times greater than anything produced in our most powerful particle colliders. The only logical explanation, something in those filaments is acting as a natural particle accelerator, flinging neutrinos across the universe with unimaginable force. Cosmic rays add another layer of mystery. The Pierre Auger Observatory in Argentina has traced the paths of the most energetic cosmic rays, protons and atomic nuclei moving at near light speed. Again, their origins trace back to filament-rich regions, not the usual suspects like supernova remnants or active galaxies. The energy required to launch these particles would demand conditions beyond anything we've observed, magnetic fields trillions of times stronger than Earth's, or shock waves spanning millions of light years. One provocative theory suggests dark matter might be the unseen architect. If certain dark matter particles decay or collide within filaments, they could unleash bursts of energy capable of birthing these extreme particles. Alternatively, filaments might harbor relic magnetic fields from the early universe, twisted and amplified over billions of years into cosmic-scale particle slingshots. The most tantalizing possibility, these hotspots could be evidence of topological defects, knots in spacetime itself, left over from the Big Bang, unraveling and releasing energy as they decay. What makes these particles invaluable is their ability to map the invisible. Unlike light, which scatters or absorbs, neutrinos and cosmic rays barrel straight through gas, dust, and even entire galaxies. By tracking their paths, we're essentially X-raying the cosmic web, revealing hidden structures no telescope could ever see. Already, neutrino data has hinted at previously unknown filament branches, while cosmic ray patterns suggest some filaments are far more turbulent than their serene appearances suggest. The implications stretch beyond astrophysics. If filaments truly accelerate particles to such extreme energies, They could be the source of rare, ultra-high-energy cosmic rays that occasionally strike Earth's atmosphere with the force of a baseball pitch, packed into a single atomic nucleus. Understanding these processes might even unlock new physics, challenging our models of particle behavior at energies unattainable in any lab. For now, every neutrino flash and cosmic ray strike is a breadcrumb leading us deeper into the cosmic web's secrets. These ghostly messengers remind us that even the emptiest stretches of space are alive with unseen activity, and the filaments weaving the universe together might be far more than silent scaffolds. They could be the universe's most powerful particle guns, firing mysteries at us from the dark. Supermassive black holes aren't just lurking in galaxies, they're aligning like compass needles across the cosmic web, pointing eerily in the same direction despite being millions of light years apart. Picture 100 scattered clocks, each with hands spinning in perfect sync without ever touching. That's the uncanny discovery astronomers made when studying black holes embedded in filament galaxies. Their spin axes often match, as if orchestrated by some unseen cosmic conductor. This isn't random chance. The probability of such alignment happening naturally is less than winning the lottery 10 times in a row. So what's forcing these cosmic titans into lockstep? The roots of this mystery might stretch back to the universe's infancy. One theory suggests primordial spin, a preferred direction, imprinted on space-time during the Big Bang itself. Imagine the newborn universe as a swirling vortex, its rotation subtle but pervasive. As matter clumped into filaments, this spin could have been preserved, funneled into black holes like DNA passing from parent to child. Supporting this idea are simulations showing that early quantum fluctuations, stretched to cosmic scales during inflation, might have created regions with coherent angular momentum pockets of the universe where everything spins the same way. If true, aligned black holes could be fossils of that initial spin, their axes frozen in time like cosmic weather vanes pointing to the universe's first moments. But there's a wilder possibility: holographic influence. Some theorists propose that black hole alignments are shadows of a deeper, higher dimensional reality, like flat silhouettes on a wall hinting at a 3D object. In this framework, filaments might be projections of a cosmic hologram, where events in a boundary dimension like the edge of the universe dictate behavior in our 3D space. If correct, aligned spins would reflect information encoded on this distant surface, making black holes pixels in a universe-sized display. While controversial, the math behind holography has successfully predicted other cosmic phenomena, lending weight to the idea that the universe's largest structures could be governed by rules we've yet to grasp fully. Yet skeptics argue for a more local explanation: tidal torque. As galaxies slide along filaments, the gravitational pull of these massive threads could slowly twist their central black holes into alignment, like pebbles rolling downhill until they all face the same way. Observations show some promise here. Black holes in denser filament regions do exhibit tighter alignment, but the effect can't fully account for matches seen across vast, disconnected spans of the web. The implications ripple far beyond curiosity. If primordial spin is confirmed, it would rewrite our understanding of the Big Bang's symmetry, revealing a universe born with a built-in twist. Holographic influence, meanwhile, could upend physics entirely, proving reality is far stranger than our 3D senses perceive. Even the tidal torque model challenges assumptions about how subtly gravity shapes cosmic evolution over eons. Every aligned black hole is a clue, a silent witness to forces that might span dimensions or epochs. And as telescopes like the Square Kilometre Array come online, mapping spins across thousands more filaments, we're not just studying black holes, we're reading the universe's hidden handwriting etched in the spin of its darkest giants. Some galaxies aren't just drifting along the cosmic web's filaments, they're racing toward them at speeds that defy gravity's grip, as if pulled by something beyond the visible universe. This bizarre motion, dubbed dark flow, was first spotted in 2008 when astronomers tracked hundreds of galaxy clusters hurtling in the same direction at over 800 kilometers per second, far faster than the expansion of space alone could explain. The culprit, an unseen gravitational titan lurking in the cosmic shadows, possibly beyond the edges of our observable universe. The most famous candidate is the Great Attractor, a mysterious region of space roughly 250 million light-years away, whose gravity appears to be yanking entire galaxy clusters off course. But here's the twist: even the Great Attractor's immense pull can't fully account for the scale of dark flow. Some researchers argue the motion points to something even grander, an exocosmic structure like a neighboring universe or a supermassive black hole from a prior cosmic cycle, exerting gravity across the fabric of spacetime itself. Imagine our universe as a ship caught in the wake of a passing vessel, its invisible wake tugging us toward uncharted waters. Critics, however, dismiss dark flow as a measurement error or the echo of ancient cosmic collisions. They point to the Doppler effect, the same phenomenon that makes a siren's pitch change as it passes, arguing that peculiar velocities within galaxy clusters might mimic large-scale flow. But when the Planck satellite mapped the cosmic microwave background in 2013, it found faint temperature shifts aligned with the dark flow direction, lending credence to the idea that something out there is pulling us. The debate hinges on a fundamental question: is our universe truly isolated, or are we feeling the gravitational whispers of realms beyond our cosmic horizon? If dark flow is real, it challenges the cosmological principle, the idea that the universe is uniform on large scales, and hints at a cosmos far more interconnected or even infinite than we've dared to imagine. For now, every anomalous galaxy motion is a breadcrumb, leading us toward one of cosmology's most existential mysteries: what lies beyond the edges of the map we've drawn for ourselves. The Cosmic Webs filaments don't just connect galaxies, they mirror the branching patterns of life itself. Stretch a neuron from the human brain alongside a filamentary map of the universe, and the resemblance is uncanny. Both fork into delicate, repeating tendrils, splitting and rejoining in ways that feel almost algorithmic. This isn't mere coincidence. From the veins of a leaf to river deltas carving continents, nature adores fractal shapes that repeat at every scale. But when the universe itself adopts these blueprints, it begs a haunting question: are we seeing random chaos or the fingerprints of something deeper, a hidden code woven into reality's fabric? Zoom out far enough and the parallels grow stranger. The same mathematical rules governing how blood vessels optimize oxygen delivery also predict how filaments funnel gas to galaxies. Take the Murray's law of physiology, a principle stating vessel diameters adjust to minimize energy loss. Apply it to cosmic filaments and the math holds. Thicker strands branch into finer tributaries with eerie precision, as if the universe and biology share an invisible engineer. Even stranger, simulations show dark matter clustering into fractal-like hierarchies, with smaller filaments nesting inside larger ones like Russian dolls, echoing the way trees branch from trunk to twig. The most tantalizing clue lies in the numbers. When physicists analyze filament networks, they find dimensions hovering around 2.5, not a solid 3D structure, not a flat plane, but a fractional in between. This fractal dimension matches patterns found in everything from lightning strikes to ocean currents, suggesting a universal language of efficiency. Energy, whether electric or gravitational, seeks the path of least resistance, sculpting forms that balance spread and connection. But here's where cosmology diverges. Unlike a lightning bolt's fleeting flash, filaments persist for billions of years, their stability hinting at a deeper equilibrium between chaos and order. Could this imply a cosmic program running behind the scenes? Some theorists play with the idea of the universe as a computational system, with filaments acting like data streams between galactic nodes. It's a provocative metaphor, but the math resists simplification. While fractals abound in nature, their cosmological versions are messier, warped by dark energy and quantum randomness. Yet even this turbulence might have purpose. Recent studies of filamentary gas show vortices and eddies resembling fluid dynamics, as if the universe isn't just structured but flowing toward some unseen equilibrium. The most radical interpretations go further. If fractal filaments reflect a fundamental law, they might bridge quantum and cosmic scales, a concept called scale symmetry. Imagine zooming into a filament substructure and finding miniature versions of the cosmic web, down to Planck-length threads vibrating with primordial energy. String theory toys with this idea, proposing that spacetime itself is built from tiny, vibrating filaments. If true, the universe's largest and smallest structures could be facets of the same phenomenon, like a hologram where every fragment contains the whole. For now, these patterns remain a beautiful enigma. They don't yet rewrite physics, but they whisper that the universe's order might be richer, more recursive than we've dared to dream. Whether fractal filaments are cosmic accidents or echoes of a deeper logic, one thing's certain: the universe loves to repeat itself, from the branching of a tree to the sprawling web that binds the stars. And in that repetition, we might just find the keys to reality's deepest secrets. Dark matter should be everywhere in the cosmic web's filaments. According to our best models, these vast threads ought to be sheathed in massive halos of invisible mass, cradling galaxies and sculpting the universe's structure. Yet when the James Webb Space Telescope turned its infrared gaze toward certain filaments, it found something startling: ghostly stretches where the dark matter halos simply aren't there. These cosmic threads stretch across the void like bridges with no supporting pillars, defying the lambda-CDM model that's been the backbone of cosmology for decades. If dark matter is the universe's invisible scaffolding, why are entire sections of the framework missing? The lambda-CDM model, short for lambda-cold dark matter, predicts a universe where filaments form a near-perfect web, each strand wrapped in dense cocoons of dark matter. Supercomputer simulations show these halos should act as gravitational anchors, pulling gas and galaxies into alignment along their lengths. But JWST razor-sharp images reveal filaments that look more like fraying ropes, with gaps where the expected dark matter overdensity fails to materialize. The discrepancy isn't trivial. In some regions, up to 70% of the predicted halos are absent, leaving galaxies adrift in structures that shouldn't hold together without dark matter's glue. One possible explanation dances on the edge of heresy. What if dark matter isn't as cold as we've assumed? The cold in CDM means particles move sluggishly, clumping easily into halos. But if some dark matter is slightly warmer, zipping through space just fast enough to resist clustering, it might explain why certain filaments appear threadbare. Alternative theories go further, suggesting dark matter might interact with itself through unknown forces, dissipating energy like cosmic friction to smooth out halos over time. Then there's the observational conundrum. JWST empty filaments often coincide with regions where the gas is unusually turbulent, as if some violent event, a long-ago galaxy collision or black hole outburst, scoured the dark matter away. Supporting this, some filaments near active galactic nuclei show faint X-ray echoes, hinting at ancient explosions powerful enough to blast dark matter particles into the void. But critics counter that even the most catastrophic events shouldn't purge halos so thoroughly. The forces required would tear galaxies apart, yet these structures remain oddly intact. The most tantalizing and unsettling possibility is that lambda-CDM, for all its successes, might be incomplete. The model nails the universe's large-scale structure, but could be missing finer details about how dark matter behaves in lower-density environments. If filaments without halos prove common, we might need to tweak the model's parameters or even consider exotic additions like self-interacting dark matter or warm dark matter hybrids. For now, every halo-deficient filament is a cosmic whisper, hinting that our understanding of dark matter, and by extension, the universe's architecture, might be due for a revision. As JWST peers deeper into these ghostly threads, we're left to wonder, are these gaps observational flukes, the scars of forgotten cataclysms, or something far stranger, a crack in the foundation of modern cosmology itself? The cosmic web's filaments hum with a hidden rhythm, sound waves from the universe's infancy, frozen in time like grooves on a cosmic record. These are baryon acoustic oscillations, ripples born when the newborn cosmos was a seething plasma of particles and energy, so dense that sound could travel through it at half the speed of light. Picture the early universe as a bubbling cauldron with pressure waves surging through the hot soup, compressing matter into peaks and troughs. When the universe cooled enough for atoms to form, these ripples, stretched by expansion, were etched into the fabric of space, leaving behind a faint fingerprint. Galaxies clustered at regular intervals along filaments, spaced roughly 500 million light-years apart like beads on an invisible string. But here's the twist: when astronomers measured these spacings, they didn't quite match the predictions. The oscillations are there, yes, but their sound is off-key. Some filaments resonate at frequencies suggesting the early universe was hotter or denser than our models account for, while others show unexpected harmonics, as if extra forces were tugging at the primordial plasma. It's like playing a centuries-old piano and discovering some keys produce notes that shouldn't exist. The discrepancy might lie in dark energy's influence. These oscillations are supposed to be pristine relics, their wavelengths stretched but otherwise unaltered by later cosmic events. Yet recent surveys like Decipher reveal filaments where the spacing contracts slightly, as if dark energy, already at work in the universe's first few billion years, subtly warped the oscillation's imprint. Others point to neutrinos. If these ghostly particles were more massive than we thought, their gravity could have nudged the ripples off rhythm. Even stranger are the echo voids, regions where oscillations vanish entirely. In a perfectly uniform universe, baryon waves should leave symmetrical peaks and troughs. But some filaments flank voids so empty they disrupt the pattern, like a singer missing a beat. One theory suggests primordial black holes lurking in the young cosmos might have absorbed enough mass to distort the waves locally. Another posits cosmic strings of hypothetical flaws in spacetime, slicing through early plasma like a knife through water, leaving scars that altered the oscillation spread. The most tantalizing clue comes from the cosmic microwave background. Its faint temperature variations map the original ripples with exquisite precision, yet when compared to today's filament spacings, subtle shifts emerge. It's as if the universe's soundtrack slowed down in certain sectors, hinting at unseen structures or forces tugging at the cosmic web over billions of years. Whatever the cause, these discordant oscillations are more than cosmic static. They're a challenge to our understanding of physics itself, written in the spacing of galaxies and the silence between them. From spinning filaments to missing dark matter, from ghostly primordial hydrogen to black holes moving in eerie synchrony, the cosmic web's 25 mysteries don't just challenge our understanding of the universe, they tear up the rulebook entirely. These filaments, once thought to be mere backdrops, have emerged as the universe's master architects, shaping everything from galactic spins to the flow of time itself. They defy gravity, warp spacetime, and hum with echoes of the Big Bang, forcing us to rethink not just how the cosmos is built, but how it lives, breathing, evolving, and whispering secrets we're only beginning to decode. Consider the contradictions we've uncovered. Filaments should be cold, yet some blaze hotter than stars. They should be static, yet they spin like cosmic tornadoes. They should be dark, yet they glow with the light of ancient quasars. Every discovery peels back another layer, revealing a universe far stranger, more dynamic, and more interconnected than we ever imagined. The cosmic web isn't just a structure, it's a living puzzle, one where dark matter's invisible hand, dark energy's relentless push, and the echoes of creation itself collide in ways that still leave scientists speechless. And the grandest revelation of all, these filaments bind us to the atoms in your body, the stars in your sky, even the device you're watching this on. All were forged in galaxies strung along these threads, part of a tapestry stretching back to the first flickers of time. To study the cosmic web is to trace our own origins, to glimpse the scaffold that cradles every story the universe has ever told. So now it's your turn. Which mystery pulled you deepest into the cosmic web's enigma? Was it the missing baryons hiding in plain sight, the filaments spinning faster than laws should allow? Or the chilling possibility that dark energy is quietly unraveling it all? Drop your thoughts below, and if these cosmic threads have left you hungry for more, hit subscribe. The universe's greatest puzzles are still waiting, and the next revelation might just rewrite reality as we know it.